we can segregate just by looking at the formula. Ionic compounds, how do we know we have an ionic compound?
You have a metal and a non-metal?
Perfect. So I think the only exception to that would be when I have ammonium ion, right? Or NH4 plus a non-metal, right? The only exception I can think of to that. You're basically looking for a metal, because that makes it unique from both of these two. Yeah, so we could underline metal. Binary covalent. How do we know it's binary covalent?
So a non-metal plus a non-metal?
Non-metal plus a non-metal. So I didn't see a metal. I saw non-metals, binary covalent. And the only exception to this would be the special case of an acid, which has hydrogen is specifically on the left. So you want to look for hydrogen on the left side of a compound, plus typically a non-metal. So by formula, we should be able to check which is which, right? Can you guys see the worksheet again?
Yes.
All right, so it's number 1. What do you say? What's your prognosis?
So it has ammonium.
Yes.
So that would be ionic?
That one's ionic. So that's a special case. It's all non-metals. It's nitrogen, hydrogen, phosphorus, oxygen. But you see this is a special case where a group of non-metals acts like a metal. So that one's kind of, we have an exception right off the bat, but that one's ionic. What about 2? I think they get easier after that.
That's covalent.
Covalent, 3.
Also covalent.
Good, 4.
That's ionic.
Good, 5.
Covalent.
Yeah, so this one's interesting too, because silicon is actually a metalloid. So maybe we should go back to the worksheet. I hope you don't mind if I flip back and forth. Is that okay? But we should also have usually metalloid plus a non-metal would also be binary covalent. Technically, if it's a metalloid on the right, you know that division? Where's my division? Let's show a periodic table. This one's kind of beat up, but okay, silicon is on this side. So it's now, even though it's a metalloid, it's on that side. For naming purposes, it's a non-metal. You got it? Whereas if I had germanium, let's say antimony. Antimony is also a metalloid. Which side is it on? It's on the left of this. See this zigzag divider?
Yeah.
So I'm going to treat these like a metal. At some point, we have to make an arbitrary decision, and that's where it splits. Talk about metalloids, and this is a really picky rule. So silicon's on the right, it's a non-metal now for naming. Antimony's on the left, it's a metal. Does that make sense? Hopefully.
Yeah.
Okay, where were we? So we said silicon chloride was
It's covalent.
binary. I'm gonna treat it as a binary because silicon is a metalloid. It's on the right side of that division. What about 6?
Covalent.
No.
Nope.
Wait, I'm sorry, what was 5?
5 was covalent. What was 6? So, okay, let's stop for a sec. Okay, so 5 is covalent because why? Why is 5 covalent?
Because of silicon, you're treating it because it's on the right.
It's on the right side of that division, so it's going to be grouped with the non-metals. It's a metalloids go across both sides. They're kind of in between. But in terms of naming, the convention as far as, this is a very picky example. As far as I understand it, if I'm on the right side of that division, then I'm going to treat it like a non-metal. So silicon's considered a non-metal for naming. Okay, what about 6?
Is it an acid?
Yeah, 6 is an acid. I have hydrogen on the left. What about 7?
Would it be ionic?
Ionic, calcium's a metal. 8. These are actually some really good examples.
Covalent.
Yeah, it's covalent. So boron, it might be considered well, it's actually not really a metalloid. I think it's a non-metal, even though it's, right on the division line. 9.
It's an acid. It's phosphoric.
Yeah, acid. Now, actually, I guess this is later. Well, I guess we're going backwards, but that's what you do when you're looking at a formula and you're going to a name. Okay, so let's go back to the camera. So for ionic, the very simple rule is it's the cation name plus the anion name. And technically from that, you remove the words ion. If it's an individual cation, then the name should end with ion. If it's an individual anion, it should end with the name ion. Calcium ion, chloride ion. But if I put them together, then I just say calcium chloride, right? Remember, for ionic compounds, no prefixes. The net charge has to equal 0. With the exception of probably the mercury 1 ion, you should have no common denominator. So if I say Ca2F4 for calcium fluoride, I say, there's a common denominator. I'd have to divide it out and make it CaF2, right? The charges have to equal 0. So also, don't show charges for compound, right? When they come together, so you can have calcium 2+ by itself and fluoride ions by itself. You need to show the charges, but when they come together to make a compound, no charges shown, right? Okay. So that's the rule. Let's just keep this page. I'm just going to keep this as my rule page. For the binary covalent, which is non-metal plus a non-metal, or a metalloid plus a non, this one, the first element, it's the element name. Let's put some stuff here. And then for the second element, it's the element root plus IDE. And then the second element always has a prefix. And the first element will have a prefix if 2 or more. And then our prefixes are mono, di, tri, tetra, penta, and then hexa, hepta, octa, nonna, and deca. So acids, there's two kinds of acids. There's binary, which has the formula HX, or perhaps H2X. And so binary are always hydro. You always start them with hydro, and then the root of the other element, and then you always say ic acid. A little note for this. So for the case where it's 2 hydrogens with a group, this guy would be a group 6A anion, and this would, and just hydrogen would go with a group 7A, right? Fluoride, chloride, bromide would be -1, so they'd only take 1 hydrogen. Oxide, sulfide, selenide, telluride would have a -2 charge. And so these ones, the root for the 6As get 2 syllables. So maybe that, it's kind of like a little sub rule. So then there's the oxyacids. The oxyacids basically have 3 things. They're going to have hydrogen, some amount, a nonmetal, and then some amount of oxygen. All right. And so for the oxyacids, take the root of the ion. Take the root of the ion, which means you remove the 8 or the, and then you add ic acid plus ic acid if it came from an 8, or the root of the anion plus us acid if it came from an ite. So all of the anions that make oxyacids either end in ate or ite, like sulfate or sulfite or nitrate or nitrite. And then a kind of a special rule for this one, maybe I can just, the ones I can think of, there's probably some weird mnemonic for this, but carbon, sulfur, phosphorus, I don't know if I can think of any others. They get 2 syllables. They get an extra syllable from the element name tossed in. Okay, so acids are trickier, and that's fair. We should be able to go from a formula to a name and a name to a formula. So how about sulfurous acid? Can I go backwards from sulfurous acid? Maybe we should do the binaries. The binaries are easier. This one is, wait, is this a binary or an oxyacid? We know it's an acid. It has acid in the name, right? Is it a binary or is it an oxyacid?
An oxy?
Yeah, good. How do I know it's an oxyacid?
Because of the OUS at the end.
Well, actually, I mean, we could have, okay, what about phosphoric acid? Is that an oxyacid or a binary?
It's an oxy.
Yeah, good. So this one doesn't have, so, but wait, it doesn't have OUS, but both of these are oxyacids. How do I know? Both, these are oxy.
They're OUS or IIC, right?
Well, but yeah, but the binaries also end in ic acid. So how do I know that one's not binary?
They don't have the hydro in front of it?
Yeah, no hydro. If they don't have hydro, then these both are oxy. So if it's phosphoric, it came from phosphate. Yeah? And so then I have to know phosphate. I have to say to myself, okay, phosphate is PO4 3 minus. There's kind of a decision tree. So if it's an ic, then I end with an 8. That's kind of the first step, right? I guess that's actually the first. Actually, let me rewrite this. Okay, so phosphoric. Let's do phosphoric acid. Phosphoric acid. So the first step is actually saying to ourselves it's an oxyacid because there's no hydro. That would be actually better first step. Okay, no hydro. So then the next step is to say the anion is, second step, phosphate, because it came from an ic. ic from an 8. Let me move this over. So then I'm going to find the formula for phosphate, which is PO4 3 minus. And so for this, it's either a chart or memorize. Right? This bridge between phosphate and its formula. So it's a lot of steps. I go through this kind of quickly in the lecture, but here we are. Then the next question is how many hydrogen ions to equal 0? How many hydrogen ions do I need to?
3.
3.
Yeah. 3 H pluses. So then finally 5 formula.
It's H3PO4.
H3PO4. We could go backwards with that. Should we go backwards? Let's go backwards. How about, let's keep the rules here. H2 SO3. So the first step, what kind of acid is this?
Oxyacid.
Good, it's an oxyacid. Second step would be, what's the anion? Can I pull this thing apart? I want to rip it apart. What is it? What's it made out of? It's made out of H plus something else.
SO3.
SO3. And then I could actually find the charge. What's the charge of SO3 have to be?
2 minus.
Minus
Good.
2.
Perfect. Right? Because technically I'm doing a reverse swap and drop. The 2's going up there. And there's that 3 is the number of oxygens, but there's 1 SO3, and so there's a 1 going up there, right? And technically there's 2 H pluses, yeah? So then, okay, I found the anion. Next step, what's the name of the anion? What is that anion? So again, we probably have to use a table or memorize. So I'd have to recognize that. There, I can give you, there's a small set of ions that I find super interesting for tests, and I can give you that list. And that's what I think would be best to do. Okay, so this one, anybody know that one or recognize it?
Sulfite.
It's sulfite. Good. So if it's sulfite,
It goes to OUS.
yeah. So this is, and actually this is a special case. So let's add another step. So because it's sulfur, it gets 2 syllables. Did I do that on the, I'll flip back on the other one because the phosphate was, let's see where the syllables came in with that. So this is actually sulfurous. I don't say sulfus acid. That would just be, so I mean, normally that's what you do. You remove the ite and you add us, but sulfur, you get 2 syllables. So there's 2 syllables, sulfur, and then name. Sulfurous acid. Yeah, okay. Let's go back to the previous one. Where was the 2 syllable thing coming over here? So we had, well, so we said phosphoric acid, it's oxy. So we still had, when we went from phosphoric, we still saw phosphate. This was still a case, it was going from 2 syllables to 1, going backwards, right? I mean, I'm being really picky here, but this is phosphoric. So I don't just say phosphorate, right? I lost a syllable. It just becomes phosphate when going backwards. That's the oxyacids. The binaries, I think, are much easier. Well, if you get something like HF, what do? How would I name that? So it's going to be hydro.
Fluoric.
Yeah, and it's FLUO. It's a fluor instead of a flower. Hydrofluoric acid, right? So fluor is the root.
One of these, would you have to describe whether it's covalent or just say it's an acid?
I would just say it's an acid. You know, I don't know if that will come up. I don't even know. You know, I put that in. That was in like a quiz or something, and so and then people were writing covalent, acid, and these kinds of things. And I guess technically that could be a test question, but in another sense, you know, what I was really trying to do was get you to think of before you start is, you know, what naming system am I going to apply? That was really what it's about. It wasn't to grade you on, ooh, I know it's an ionic, or ooh, I know it's covalent. I mean, we could ask a question like that, but it was really for me to get you to jog you guys and say, okay, decide which system. Because I see people that don't practice enough mix up the systems. That's usually one of the more common errors. So we could practice more acid problems, or we could look at some of the other ones, or we could do
How
something.
about the difference between the base and acid? Because that came up on one of them.
In terms of naming?
Well, like what's the difference between a base and an acid?
I know, and actually we really haven't, I mean, so for net ionic equations, we really actually haven't covered acids and bases yet, but what I'm calling an acid is simply something that has hydrogen on the left. It's specifically put on the left of the formula, plus non-metal, right? So that one's straightforward. For us, a base is just a special case of an ionic compound. It's a metal plus hydroxide. That's what makes a base, right? So HCl is an acid, NaOH is a base. I have a metal hydroxide. Hydrogen on the left means it's a hydrogen ion plus a chloride ion, right?
If you have a base, you'll just say it's an ionic one. It's not.
Yeah, there's other cases of acids and bases that there are ionic compounds that can act acidic, and there are ionic compounds that can act basic. So like NaH2PO4 is technically acidic, right? But Na2HPO4 is basic. And you may get into this in this kind of controversy in Chem 1A, or probably more likely you'll get into this in depth in Chem 1B. So just having hydrogen on the left or hydroxide on the right is it's not the end of the story. Ahead, we're going to cut like ammonia, NH3 technically is a base. And what it will do is it can react with water and then make NH4OH, which is technically a metal and hydroxide, right? But there's a lot more acids and bases. There's just a lot of material on it, but it's not